Okay, so today we're going to be talking about a part. We're going to start to look at how you might get information from a datasheet such as this. This is a Toshiba datasheet, and there's infinitely many datasheets we could choose from, but this one was of interest to me in a previous project. There's going to be a lot of motor control projects coming up, especially as you get things like UAVs and quadricopters and different various pumps and all of this stuff. So I figured it was a good place to start. This is the Toshiba TB9061AFNG. The A in this stands for automotive. Most of the work that I did was in the automotive industry, so it has the most interest to me. So this product or this model may not mean a whole lot to you, but I'm trying to show basically how you would pick out information, how you might use it practically in your engineering. When you take a data sheet, it's generally not enough to just look at the data sheet and then try to design off of it. You're really going to have to take all of the values from the data sheet and put them in either an Excel sheet or a Word document, which is what I like to do, and then be able to operate on that information to be able to come to the right conclusion or right design decision, which may not be this part. It may be a different part, but being very careful and meticulous with the data is important. So we're gonna kind of jump right in here with some of the basic summaries. We may go detailed, but today it's just going to be the first 2 pages or so. So we start with the overall size of it. This is a shrink package. It's an SOP 24. 24 is the amount of pins, and the shrink outline provides just a little bit flatter of a depth. So this will probably be the lowest sitting IC on your board. Among all the ones you might have. The weight is about 140 milligrams or 0.14 grams. The weight of it doesn't typically matter for many water pumping or for automotive applications because its weight is neglected with respect to the weight of all of the other objects, but some customers may specify that a weight requirement is necessary. So you might have to do a quick calculation of all of the components on your board and the PCB, and then all of the metallic components, and then be able to quote this. Where this would affect you is if this was in a UAV of some kind, because you might have more weight on one side of the board, whether your board's rectangular or circular or triangular, whatever geometry it is, but that might affect you. So sometimes paying attention to the weight is interesting, or mechanical engineers will ask you for this type of data as well as the geometric data. Most softwares now will allow you to produce a 3-dimensional model from your 2D schematics, and then you can hand that off to the mechanical engineers, and they'll be happy to just receive that model and then put it in the larger assemblies. That's how it worked in the office that I was in. So we'll go through the features of this device. It's 3-phase and it's full wave sensorless. The sensorless means that it doesn't take in Hall effect sensor data, and that it gains its information from the back electromotive force, which is essentially when you run a motor, there's a dissipative mode, which is what you think about when you're trying to move some type of load, like let's say the Tesla is trying to accelerate. But there's also the generative mode, which means that if you were running an alternator, you're going to be gaining some type of energy from the cyclical motion of the rotor within the stator. So when you're running a motor, you're running it in dissipative mode and you're rotating it in generative mode. And the generative mode is where you get the information about where the rotor is with respect to the stator. This is how you can do this without any type of external sensing to gather that information. But it does come at the cost or the disadvantage of not being very good at low speeds, because you can't tell the rotor's position with respect to the stator at low speed, and you can't tell how fast it's going or in what direction. Could be going clockwise or could be going counterclockwise. So the strategy of this integrated circuit is to jump start the rotor in one direction and then say, okay, it's rotating clockwise or counterclockwise. Now what do I do with it? It uses an open loop control commutation scheme, basically forcing it and saying, like, I want it to be rotating clockwise at this particular RPM. And then once it gets the back EMF signal, it will close that loop, and then you'll be able to control from there. So that's a little bit ahead of myself, but the PWM chopper drive, this is what allows you to change the amount of power, which could translate to the speed of the motor course, if the load increases, then your power is going to be drawn from the battery. But basically, this provides a speed control, or the means for speed control. There's outputs for external P channel and N channel. So I'll go down to the schematic, or the application schematic of how this is supposed to work. There's a lot to this data sheet. I don't know how much we're going to be able to go through all of it, but basically, this is one phase. You have the MOSFETs here. You choose these MOSFETs external to this device. This device provides just pre-drive and control. It does not actually do the driving aspect of it, which is how you connect to the motor. But in the high side and the low side, you can see this arrow is pointing out, so that's going to be the P channel MOSFET. And this arrow is pointing inward, which is going to be the N channel MOSFET. This has the advantage of being able to apply some voltage here that's hopefully lower than the gate source voltage here, but then allows you to go to ground signal and be able to turn it on. So low signal here is going to be on, and high signal, which matches VB, is going to be off. So P channel, N channel, this sort of complementary CMOS technology allows you to be able to control where you want the direction of the current. And of course, there are two more phases of that. So it's just telling you that up front, hey, look, you need to connect me to a P channel, and you need to connect me to an N channel on the low side. There are techniques that you can use to convert this upper P channel to an N channel, but that's perhaps for another video. So next item of the things that this integrated circuit can do, it can provide PWM input. That's going to control that chopper drive. So I can use a PWM signal to control a PWM signal, and then it basically just exchanges the duty cycle, and that provides a speed control. Or I can use an analog input. Now we use the analog input of this device in the lab, but we prefer the PWM input. And most of the times, your customers are going to want some type of either PWM signal at the very least, or they're going to want some sort of diagnostic interface like CAN or LIN or something of that nature. Moving down, you have the rotating direction, so you can decide if you want this to be clockwise or counterclockwise. If this is a pump, the impeller is generally going to be connected in one direction. So that means the chirality of the vanes on the pump are going to be a certain direction to maximize the flow. So you have some sort of hydraulic efficiency, and you put these vanes or these like propeller blades in the water, and it's going to scoop the water and push it in the direction of the line. So typically you're not going to be going counterclockwise, you're going to be going clockwise. However, if somewhere down the connections somebody made a mistake, or they wired one phase, like let's say they didn't serialize their phases A, B, C, or UVW, and let's say they wired it A, C, B, or something like that, you could correct that by changing the clockwise direction. So this can be helpful sometimes in a design decision, but alternately, like you're not going to, ultimately you're not going to use one. You're not going to use one and the other in a single application. You're going to use one or the other, and then you're going to stick with that. And then if there's anything outside of your control that changes the direction of the pump, you're going to be choosing this other one. This can be useful if you're microcontrolling this. So you have the microcontroller that's going into the pre-driver. Thank you. Okay, so PWM control on the lower drive output, that's just telling you what's going to be doing the chopping. So we look at the signal here, roughly speaking. It's saying that on the low side, this is what you're doing. You're chopping this up, and then your overall signal is going to be looking like that. This P channel is going to be quite long in terms of speed signals goes, and the output you can modify pretty quickly. So the frequency of this PWM signal is going to be higher with respect to this one. And you have your windows, so this output goes high, which is the same as off, because it's a P channel device in the high side, and this is setting your PWM. So that's one thing we can get into. We can go further into this if you'd like. Next thing, so we have the 8-channel A to D conversion that allows you to to use the analog feature if you want to. It captures the value and then assigns this to the PWM. You have comparators that are going to look at the voltages. It says induced. That basically means that it's a back EMF signal. And you're going to be detecting those and comparing them to some reference of minimum starting, basically saying like, oh yeah, like you've passed my phase, so the motor is this far into the rotor, so you can expect that on this quadrant, or maybe this portion of the pie, if you want to use that reference, it's past that zone, so now you can change the winding so that it's going to produce an either attractive force or a repulsive force to modify that rotor as it's commutating around. You have an overcurrent detector. Overcurrent is interesting. You like to think of it sometimes where you're going to be measuring current directly. You're not actually. The application circuit is going to be using what's called a sense resistor, if you're unfamiliar with that. So in this diagram, it doesn't really show you very well because it's just showing the high side and the low side. But in an actual application, you're going to have another resistor here before you go to ground, and that's going to convert the current that gets aggregated through each of these lines, and then it's going to manifest the voltage. So for instance, if I have a current that's going from B here, you have this little choke inductor, and then the current is going through these. It could be going from A to B, and so it's going through the motor this way, the motor windings, and then the current that goes through it is going to pass through RS. RS is sufficiently low and sufficiently high, so it's going to be somewhere around maybe 10 milliohms, enough to be able to indicate, but not too much to dissipate, because you don't want to waste energy through that resistor. So you're just trying to capture information about the current conditions. You're not trying to actually power this or heat anything from it, although I suppose you could. So anyway, it manifests a voltage, and then this OC detect line is going to compare that voltage to some type of internal reference. Here they have some type of filtration, so that helps to stabilize the voltage, because the current might have some sort of spikes on it or some type of noise, and that's just to make it so that this overcurrent detection isn't too sensitive to that effect. So let's go into it. See if I can find the diagram. I don't have this memorized. I've used it a lot, but I don't have the individual pages memorized. I think that's what we want right here. So you have overcurrent, and then you see that these are the comparators. So these are internal references that come off of the power supply that you connect to. One is 100 millivolts, the other one's 200 millivolts, and so you set it, and then these get triggered. This one goes into some sort of limping mode. It's like a fail-safe. So if I trigger this one but not this one, it's going to go into this kind of limp mode where it's going to cut off the power every cycle. Whereas if I trip this, it's going to actually turn off the motor entirely. And then it's going to time out until you either power cycle the device or some other type of condition alleviates, and then you're good to go. Loss of synchronization, looks for detection and automatic restart, so this improves the startup conditions. This is the downside disadvantage of this device, is that startup can be difficult, and we found that. I mean, if you look from if this is like a 100-watt pump or less, this IC will work perfect for that application. But if you're starting to draw more current, or you're trying to use voltages that are higher than normal, you have to do some weird and tricky stuff to get your motor to work reliably. And this loss of synchronism is supposed to help with that. I'm not sure if I ever used that feature or observed that feature, but I'm sure it's better than what it was before. You have an internal oscillator, provides the pulse width modulation, and a few other things. It has a built-in 5-volt constant voltage circuit. You have this power supply here. You put it into VB, and then you get VReg. So it allows you to use 5 volts for something. Like you might take this 5-volt thing and you might swing it over here at the this is force commutation frequency. So I mean, it looks like it's already interconnected. Oh no, this is just the default value. This is a default value. So anyway, I would use VReg for some other type of thing to set this, and I would use this to set my lead angle, and that's about it. That's about what I would do with that. But they give you this little power source so that you can do some basic configurations on the device if you want to. Operating range -40 to 125 degrees C. This is pretty common for most of what most customers are going to require of you for your automotive product. If this is a aerospace or military application, well, first you're not going to use this IC because it's not a military or aerospace grade, but this range gets extended. This might go to 135 and this might go to -55. So because the temperatures are more severe, or the military application requires you to make sure that your part is well overrated for whatever applications they might have for military. We already talked about the shrink outline in the 24-pin package, and they're telling you that the TB9061A is going to also fit the TB9061FNG, which is the non-automotive version. The automotive version just means that it's past this AEC-Q 100. These devices are for the most part, they're the same. There's really no big differences in these things, except that when they take a batch of parts, they might subject it to a couple more tests, and the ones that pass just naturally or through probability are going to be put in a bin of AEC-Q parts, and there's another process of documentation, or there's just a bunch of more eyes on it, essentially, that dictate that it's going to be automotive qualified. But for prototypical purposes, especially like if their customer isn't paying you to produce, thousands of parts, you can use the TB9061 during the prototypical stages and be just fine. And then as soon as you want that AEC-Q rating, okay, well, we just get this part and we populate it there instead. So this is more of a bill of materials thing. You can just exchange it on your BOM, and then you'll be fine. Last thing from a summary, you have these products are compatible with RoHS regulations and the 2011 directive. My understanding is that there's been an update to that directive, but they're saying that it meets the previous. Most customers are okay with you just meeting this, unless they're very particular about their environmental conditions. And the RoHS basically means that you don't have any weird materials like hexavalent chrome or mercury or lead or any of that stuff. So they're saying that they are compatible. In some data sheets, you'll see that they have some type of, and they have a manifest for that. Yeah, restrictions of use. I'm trying to think. Oh, I guess not. Some will have a manifest that basically certifies that product as RoHS, some type of certificate there. This device doesn't have it. So that's kind of your basic stuff. When you're going through a data sheet, you're looking at all of these little values and the features, and then you're comparing these features to a spec. Hopefully when you've done your application, you've designed your application to have some type of functional or featural requirements. It must do this, it must do that, or it must do this under certain conditions, and you've already defined that. So you create a list of all of the features that you are looking for, and then you're searching through parts that can provide those features. So there is a lot of tedious and how do I say it? It's very manual labor sometimes to be able to withdraw the information of the featural content and then compare this to what your ideal is or what you need to do. Some of the functions may be software related. You may decide, I want to implement these features in software, or I want to implement them in hardware, and I can do both. I mean, I've done software development and hardware development, and I prefer, even though I'm a software person, I prefer to do things in hardware, because then you can set and forget it, and you don't need all of the administrative processes for your software that are required, and all of the testing and all the sandboxing and all of this stuff. So my strategy has always been to keep software out of the game until you have to put it in the game. Then when software becomes a part of it, then most of your features should be in software. So then that way you can reduce your cost as much, and then your cost-benefit ratio increases in your favor. But this device was useful to be able to provide most of the feature content that we wanted. If there was any type of input requirements that the customer wanted, we might put a microcontroller to be able to change it from a LIN or CAN or whatever diagnostic interface they wanted. And then that was a pretty low-cost application. for the motor. If you're not designing the motor yourself, make sure you stay very close to what the in communication with the motor designer so that you understand if his parameters for the design of the motor are going to mesh with the control application that you have decided. That's about it for now. We'll go into more later.